Welcome to the AP Statistics. This is a dependent probabilities problem that has to do with tree diagrams to help see the probabilities and the dependence, and then also to do some probabilities. So this starts off by talking about Alice, who has stomach problems. If she eats beef, then she gets stomach aches, and that would be, it says 30% of the time. If she's offered beef, she'll eat it 60% of the time, but she gets the stomach aches 30% of the time she eats it. 40% of the time, she'll choose to eat something else. But even if she does eat something else, she gets a stomach ache 10% of the time. So hopefully when you see this type of problem, you'll see that right away we have different probabilities for different things going on. The probability of her getting a stomach ache changes depending on what she eats. So that's a dependent situation, right? It's not independent. Now, what does that look like on a tree diagram? So here I have A for Alice. Sorry, not A for eating beef, and then A complement for not eating beef. So there's a 60% chance she'll choose the beef if it's offered, 40% chance she'll eat something else. And then you'll see on the next column here that for getting a stomach ache or not, the probabilities are different. Like you should be able to see right here, this 0.3 and then this 0.1 down here are different. So depending on if she ate beef or not. So if she eats beef, 30% of the time she'll get a stomach ache, 70% time she will not. If she doesn't eat beef, then 10% of the time she gets a stomach ache, 90% of the time she does not. All right, so this is automatically, this is where you look to see, is this a dependent situation? Because these probabilities, if they were the same, then we would know it's independent. It's an independent situation because it doesn't matter what happened in the first level, the probability stayed the same no matter what. I like to put the notation up here to kind of look at that because a lot of times people get confused with the notation of things. So what you have on this whole path from here all the way to here is the probability of A and B happening, right? Where she eats beef and she gets a stomach ache. That happens 18% of the time. We use the multiplication rule to get that. So 0.6 times 0.3 gives you the 0.18. But you can also work backwards on these. And that's the hard part that people don't see. Like if I were trying to say, like someone said, oh, what's, like sometimes you're given this and maybe you're given the probability of A and you're looking for the probability of B given A. So you can actually, to get the probability of B given A, you can, which is this, right? You can take the final thing, the probability of A and B, and divide by the probability of A. And that's really weird, right? That's like, I think that's, you can see this written down here, right? So the probability of B given A is the probability of A and B both happening divided by the probability of A. When you just look at this formula, you're like, what in the world? How did they come up with that? And what does that mean? But if you just refer back to the tree diagram, I think it's easy to see that really it's just probability of A, and then this is just probability of B, but it's that probability of B given that A already happened. Because remember, this is a dependent situation. So down here, this is the probability of B happening given that A did not happen. It's the complement of A, right? So are both of these really just the probability of B? Yeah, it's just probability A times probability of B equals the probability of A and B. It just looks a little different because now you have two different probabilities of B, and you have to talk about, like, be clear about which one you're using. Are we using probability of B after A happened or probability of B after A didn't happen? Because they're different, right? They're different percentages. So that's why this whole B given A comes into it. Instead of just saying A times B gives you A and B, which we used to do, right? Okay, so there's the whole tree diagram and all the probabilities of each situation laid out. So that should make answering the problems much easier. The first one says the probability of A and B complement. Okay, here's A, so she ate beef, but she did not get a stomach ache. So that's 0.42 as a probability, right? And then we have A complement B. A complement did not eat beef, but B still happens. She still got a stomach ache, and that's 4% chance of happening. Probability of B. Oh, that's a little different. What does that mean, probability of B? There's two B's. Oh, you actually have to come over here and say, where are the situations where she got a stomach ache? So this is where she ate beef and got a stomach ache. This is where she didn't eat beef but still got a stomach ache. So both of those situations are the probability of getting a stomach ache, which are 0.22. And the only way to figure that out is by looking at the totals here and looking at all the cases where that occurs and adding them up. Okay, now we have the probability of A intersecting. So that's where probability of A and B happen. We already did that, A and B. That's 18%. You can see that. Now I have the probability of B and A happening same time. Well, that's the same probability, not a problem. It doesn't matter if you switch it around. It doesn't make any difference. This chicken scratch you see you're scribbling around here, this was just trying to use this formula to show things in different light, like to look at things differently. And like reversing the condition. Let's take a look at this reversing the condition. Okay, you can see it's written on the side here, reversing the condition. Okay, so what they're talking about is, well, let's talk about the probability of B and A, but using kind of the all the probabilities, like using the formula, right? Using that formula. So they're trying to take probability of A and B, right? Probability A and B, which we know is 18%. And then you're dividing by the probability of A happening, which we already, is it probability of A? Yeah. Oh no, this is probability of B happening on the bottom because we're reversing this, right? This is getting reversed. It's not B given A, it's A given B. So we have probability of B on the bottom, which we saw up here. And then you're supposed to multiply that, right, times probability of B. So they cancel out and you come right back to where you started, kind of thing. Don't worry about it too much. I just like people to see that this formula, what you're going to see on your notes and your sheets and stuff, and in the book, really, you just think about a tree diagram. It's just this path times this path equals the total. So if you want to look for any of these branches, you just have to take the total and divide by one of them to get the other, right? It's actually a really simple idea. Okay, so probability, this is the not independence thing, but actually showing it the way you're supposed to. So this is how you check to see if things are independent or not. Like formally, right? I can look at the tree diagram and I know, oh, this is different than this. I know immediately, I know it's dependent and it's not independent, but we want to like show it the way we're supposed to do. So probability of B given A, probability of B given A. So we're saying that, they got 0.3 here, right? So probability of 3 given A, you have to look for, if A happens, it's given A, right? So A happened, that's given A. The probability of B happening is 0.3. So what's the probability of probability of getting a stomach ache given that they ate beef, right? That's what this is saying right there. So that's 30%. And we're supposed to compare that to the probability of getting a stomach ache overall, which hopefully maybe in your mind that kind of brings you back to a contingency table and how you're comparing the individual probability to the total, right? To the marginal probability on the totals, right? So you can see this is 22, it doesn't equal 30, right? It's different, so not independent. Same thing the other way. Now this one is interesting. We need to look at this. So if you say probability A given B, you have to go back up here and say, well, given that B happened, that's this one, the probability of A as well. So given the probability B happened is actually 22%, right? We saw that earlier with 18 and 4. These are both the probability of B happening. So you'll see down here that we have it over 22%, not just one or the other. And then it says the probability that A actually happened out of the B happening. So this is the only one where A actually happened, given that B happened. So it's 18% divided by the 22%. We don't use the other ones because these other ones are where B did not happen. B did not happen, right? So we only take the ones where B happened, and then out of that, we want the one or however many where A happened. So A given B. Hopefully that made sense. So when you look here, that's what you're looking at here. It's very important. This one's a very important one here because you're going to be asked to do this. So this is your probability of B happening, right? Given B happened, what's the probability out of that A happened? Okay, and you do that, and you'll be able to show that that's not the same as the probability of A, because the probability of A is 60%. There's a 60% chance she's going to eat beef. So this seems like a little easy little worksheet on the surface, but it's got some really good stuff going on. It's noticing dependence on a tree diagram. It's going through this formula and why that works. It's kind of reversing the condition a little bit. This down here is also reversing the condition, right? And looking at the totals at the end, and because B was the given part, and we have B in two different places, we have to put those together for our total B probability. So reversing the condition is also on this little worksheet, right? Which is very useful and something you need. All right, ask questions if you have them all the time, right?